Hello, my name is Russ Burleson, and welcome to Crave the Wave, Class 3. I'll be sharing my screen right now. And so, again, my name is Russ Burleson. Below is my email. So, we're going to start off with just a really quick binder check. We're going to do an electromagnetic wave overview. We're going to talk about waves. We're going to talk about spectrum, particle and wave properties. We're going to talk about the speed equation. And then we're going to talk about the major ways that waves change direction. That'd be reflection, refraction, diffraction. Okay. We'll also talk about superposition and interference and polarization. So, as I say, every time you do a test, even if you're testing amongst yourselves, so you and your partner are getting together and running tests, see if you can find stuff within 10 seconds. With the goal being able to find everything that you are asked for within under 5 seconds. It'll tell you if you need to add more things, if you need to reorganize it, or if you need to include multiple examples. So let's find the speed of sound in air at sea level and standard temperature and pressure. Okay. Now, one thing to keep in mind, don't just do it from memory. See if you can find it in your book. What's the formula for speed of sound? It's a function of Kelvin and degrees Celsius. Okay, find both of those formulas. What is the speed? What speed is Mach 2 at 10,000 meters? Okay, so now this one may require a little bit different. You may have to look up and see what Mach means. See that it's the speed of sound. Okay, so Mach 2 is twice the speed of sound at 10,000 meters. So you would need to find the speed of sound in air at 10,000 meters. Okay. And then, okay, you double that number and you get Mach 2. What's the bulk modulus for steel? Now, this one is one to see if you have bulk moduluses of common materials. And of course, what's the speed of sound in steel? Okay. And again, what you're going to want to do is make sure that you can find these quickly and easily. So let's talk about electromagnetic waves. These are energy waves that consist of electric and magnetic fields, and they induce each other. So you'll notice that in this particular diagram, the E field is going up and down, and it's red. The magnetic field is going along the x-axis, okay, and it is blue. And then what we do to figure out which way it is propagating is that we take our right hand, we put our pointing finger in the direction of the electric field, we put our middle finger on the right hand at a 90-degree angle in the direction of the magnetic field. And then our thumb, when we put out our thumb, it's perpendicular to both. And when you're perpendicular to everything in 3 dimensions, that's called orthogonal. Okay, your thumb is the direction of propagation. So what I can see is that my E field goes up in the Z, my B field goes up in the X. So therefore, the direction of propagation is my Y direction. So let's talk about electromagnetic energy. We'll get into this a little bit more in depth later, but one thing to keep in mind is that the electromagnetic spectrum goes from very, very low, okay, to infinitely high, okay? And generally speaking, the very low areas on the electromagnetic spectrum are usually referred to as radio waves, okay? And then above radio waves, you have microwaves, and above that, you have infrared light. Above that, you have visible light. Above that, you have ultraviolet light. Okay, and those are the 3 that are usually considered light, if you will. Then you start getting into X-ray, and then above that, you get into gamma rays. Okay, And gamma rays also includes, sometimes you'll hear the term cosmic rays. So these are super high frequency. And what you want to look at is that as the frequency goes up, the wavelength goes down. They're inversely proportional to each other. So whereas some of the longest radio waves may be on the size of buildings, some of the shorter ones are on the size of a human person. So it's like 2 meters. Okay. So that's also where microwaves start. And then microwaves go all the way up to about honeybee size. Okay. And then when you're talking about the size of an infrared wave, probably talking about how, if you punched a hole in a piece of paper with a pen, how big is that hole? Then you start getting to visible light, you're talking about protozoans. Okay. And then when you get into ultraviolet light, you're talking about the size of molecules. And then X-rays, you get to the size of atoms. And gamma rays, you can get to the size of atomic nuclei. Okay. And and sometimes you'll hear us talk about electrons, and one of the reasons they'll use electrons as their for transmitting electromagnetic energy is you can change the frequency on them quite easily, and you can get very, very high frequencies. And so when when you talk about an electron microscope, you can see things much smaller than you could with like a light microscope. But you'll notice here that the spectrums here, they're the same spectrum, they're just written differently. And we want to have multiples of these. And so when we talk about a spectrum, a couple things to keep in mind. Speed of light is constant, okay? The frequency and wavelength are inversely proportional to each other. And as we said, it starts at radio and goes all the way up to gamma rays. And the frequencies that we normally talk about, like ones like for radio, for TV, for communication, you'll notice that they are in these bands that are easily transmit through our atmosphere. Now, the areas down here below where you see the large areas where it says 100% absorption, okay, those particular frequencies don't transmit very well in Earth's atmosphere. And the reason for that is a lot of different reasons. Usually there is something in the atmosphere that's the resonant frequency, so it just absorbs all that energy. Sometimes it's water vapor, sometimes it's oxygen, hydrogen, nitrogen, etc. But there are a couple of bands where waves just really transmit incredibly well, and you have these bands that are available. And so these are the ones that we quite often use. Okay, so you'll notice here for the radio waves, transmits really well, but then some of the infrared stuff doesn't transmit as well. Okay, and you'll find out that a lot of that stuff, if you do have something that's infrared, it's usually shorter distance because it gets absorbed too quickly. But of course, visible light, the stuff that we see, transmits very well. And that's because our eyes developed over a long period of time to be able to see that light, because that's the light that comes through. So let's talk about what they call wave particle duality. What that means is that when you get very small and you're dealing with these electromagnetic waves, a lot of times they're made up of particles. So are they a particle? Are they a wave? Yes, is the answer. They are both. Okay. So what James Clerk Maxwell determined was he was able to figure out how electric and magnetic fields interacted, and also how they induced current and voltage. Okay. And so one thing that I want you to keep in mind is that when you're looking at things, sometimes we'll be talking about a photon being light, and sometimes we'll talk about light being wave. Both are valid ways to look at light. Okay. The other thing to keep in mind is that if you have a change in the electric field, like we were talking about before, it'll induce a change in the magnetic field, where one's varying over time, the other one will be varying over space, and vice versa. You can just like I can move an electric field like a capacitor back and forth and induce a magnetic field change, I can move a magnet and induce a change on the electric field. And these are how things like transformers and generators and other mechanisms work. Now, you'll notice I included in here Faraday and Ampere's law, and this is well beyond the scope of this course, but I just wanted to show you sort of what Maxwell's equations look like in mathematical form. So let's talk about how fast are electromagnetic waves. Well, they're all going to be at the speed of light. Okay. Now, the speed of light is at different speeds depending upon the medium. If there's no medium, we call that free space, or sometimes I'll refer to it as vacuum. Sometimes I'll just say outer space or whatever. The speed of light is like 2.99792 times 10 to the 8th meters per second. So as you can see, to 4 significant digits, it's 3 times 10 to the 8th meters per second. Now, Russ Burleson, anytime I'm doing a test, I will always tell people to use 3 times 10 to the 8th meters per second. Okay? Because usually going beyond 4 significant digits is not really accurate. But there will be other folks that will want you to use more extended versions. Now, mind you, that's only valid in free space. Okay? Let's say we've got an electromagnetic wave traveling in a different medium. Okay? It's going to slow it down a little bit. So like air is actually a really good transmitter for most of the frequencies that we're talking about. And so the refractive index is called N. And what N is equal to is it's equal to that pure speed of light divided by the actual speed of light in that medium. And remember, in outer space, in free space, in vacuum, N is equal to 1. It's defined as 1. Okay. However, let's say we get into air, which is close to that, but not quite there. For most frequencies, it's going to be something like 1.000293. So you can see why we almost always assume air has a refractive index of about 1. Okay, we don't have to treat it like the vacuum because it's really not much different. But water is significantly different. It's like 33% different. So water, its refractive index is 1.333. Okay, cubic zirconia is like 2.15, and diamond is 2.42. In fact, a lot of the tests, if you ever see a jeweler, they'll have a test that they'll run. They'll figure out if it's pure diamond based upon the refractive index. If the refractive index is 2.42, it goes, oh, it's diamond. Okay. If it's something other than that, the cubic zirconia light will light up. And so for pretty much every material, every gas, every liquid, every solid, there's going to be a different refractive index. Okay. Some of the refractive indexes are so high, light really just can't transmit through them. Okay. So light will either reflect off of them or be completely absorbed by them. Okay. So another way that you can figure out the speed of light in any material is if you know the permittivity, which is given here by epsilon, and the permeability given by mu for those materials. And if you take 1 divided by the square root of the product of the permittivity and permeability, that will give you the speed of light in that material. Okay. Now, if you ever see epsilon naught, which is like epsilon with a 0 on it, or mu with a 0 on it, mu naught, those are the permittivity and permeability of free space, and those are just constants. Okay. And 1 over the square root of epsilon 0 times the square root of 1 over the square root of mu sub 0, that's going to be equal to that 3 times 10 to the 8th meters per second. Okay, that's going to be the speed of light in free space. Okay, it's just something to keep in mind. Okay, And as you can well imagine, now that we're in the electromagnetic world, you're definitely going to be needing to know how to do scientific notation. So let's start by talking about reflection. So reflection is probably the single number one way that we talk about an electromagnetic field, especially light, changing direction. What ends up happening is you have an electromagnetic wave or beam of light impact on a surface and bounce back up. Okay, it's not absorbed, it's not transmitted, it bounces back up. Now, if you've got a mirror that's got a really nice, shiny, flat mirror, it's going to reflect exactly like it's supposed to. Okay. And in fact, if I fire a laser at a perfect mirror, it's going to come back up with a laser. And so, one of the few laws that we have here is called the law of reflection. And what that says is that if we look up here, and we'll use theta quite a bit when describing angles. Okay, so theta sub I is the incident angle, is always going to be equal to the reflection angle, or theta sub r. Okay, that is a law. It's something you should know by heart, but it's also something that should be in your book. Okay, you'll also notice that theta sub I is measured not from the mirror, okay? It is measured from normal to the mirror. And what that means is it is exactly 90 degrees from that plane of the mirror. Okay? So when I'm bouncing off of something and I say theta sub I is 0, well theta sub I is 0 means it's coming straight into the mirror and it bounces straight back. Okay? If I say it is at 80 degrees, it's coming in at a very shallow angle and bouncing out at a very shallow angle. But whenever we talk about the angles for an interface, we're always going to be talking about the angle to the normal direction. Okay. So you'll notice here on the right-hand side, we actually can see that we're coming in at about 50 degrees. Wait. Yeah, 50 degrees. So theta sub I is 50 degrees, and we're hitting this mirror, and it's going to bounce back right at 50 degrees. And that works 100% of the time. Now you'll notice that theta sub I is a little stronger than theta sub r. And the reason for that is not all of the light is reflected. Some of it is absorbed in this block. So not every mirror is perfect. In fact, none of them, except for the mathematical ones, are perfect. Okay. But that explains specular reflection. But let's talk about diffuse reflection. So we have all been outside and a plane of glass, which is nice and flat, hits the right angle and the sunlight hits it and it bounces in our eyes and it's blinding. That's specular reflection. That's that reflection that is dead on, and it focuses the power of the sun, and however much is reflected from that pane of glass or from that mirror goes straight towards you in an eye. It's really bright. Now, we don't like that usually. That's why we wear sunglasses and all other sorts of stuff. However, reflection is very important because it's how we see almost everything. And what I mean by that is when I look at, like, I have this yellow pad of sticky notes, right? The way we see yellow is that the light impacts on this rough surface because it's not a mirror, it's a rough surface. And what ends up happening is that light goes in a whole bunch of different directions. And you'll notice here in the red lines here, it shows how the diffuse reflection. And that's why I can see this pad no matter which way it's pointed. Now there are certain directions, like right there, you'll notice it's a little brighter because that's where we get the specular refraction. So we're going to get more light bouncing still in that reflective angle, but we're going to get less light. You still get something. So any material that you see uh, is generally going to be what we'll call diffuse or rough reflective. Okay, so that's why you're able to see things, okay, and see each other. It's because the light bounces off of us. It's not like this pad of paper generated its own light. Now let's talk about refraction. Now, refraction is where we bend light as it goes from one media to another media. Okay, so what does that mean? So if we look here, I have light, and in this particular case, in the middle here, you'll notice we have a prism. I'm putting in white light. Now, white light includes all the colors of the rainbow. Okay. Now, one thing we didn't talk too much about is that the indices of, or the indices of refraction are slightly different for every wavelength. They're not exactly the same. So what will happen is that this light goes in here and it is actually bent differently depending on its color. So it's bent less for red and it's bent a lot more for violet or blue. Okay. And that's how you get the colors of the rainbow. Okay. And if you look off to the right of here in this GIF, you'll notice that we have that wave coming in and the wave turns when it hits that interface. The other thing that I want you to notice is that the speed is different. So that's what causes the light to bend, is that it's different speeds. Okay. Now, if you look at the example up above where I've got theta 1, theta r, and theta 2. Okay. So that light is coming in at 50 degrees. So theta 1 is our incident angle. Okay. And it's equal to 50 degrees. Then I look over here, theta r, by definition, by the law of reflection, is going to be 50 degrees. And actually 60 degrees, sorry, 60 degrees. But, okay, it hits a block of material. And at that interface, it bends. Now, remember, we measure the angle from the normal. So below here, I'm measuring the angle below from here to here. And so theta 2, or theta refracted, is equal to about 35 degrees. Okay? And so this guy named Snell, and this is an important law to know, okay, came up with this formula here, which says basically the sine of theta 1 divided by the sine of theta 2 is equal to the ratio of the speeds of light, or equal to the inverse ratio of the indices of refraction. Okay? It's very important that you know generally how this works as you go through regionals. Now, when you get to state and national level competitions, you're actually going to solve for these problems. Okay? The other thing to keep in mind is that if you're going from a slower material to a faster material, okay, and let's say you're underwater, okay, if I'm underwater and I'm looking up, okay, water is 1.33, so it's a slower material. Air above is 1, index of refraction, so therefore it's a faster material. There comes an angle at which everything gets bounced back. In other words, I get total internal reflection. And this is why when you're in water and you're looking at the end of the swimming pool, you can't see somebody standing on the edge of the end of the swimming pool. You can't. Now, if they were directly above the pool, you'd be able to see them. But it's actually after about 48 degrees, everything is reflected. Okay. It's also, the other thing to keep in mind is that the bending of that light is the reason why when you're looking into an aquarium or in a pool or whatever, the actual location of a fish or something else is slightly different than what you perceive it to be because the light has been bent. So now let's talk about the third way that light bends, and that is wave diffraction. Okay. So this is bending of a wave around an obstacle. Okay. So you look up above here, we have waves in the ocean. They're coming in, and we've got a little lagoon here. Okay. But these rocks protect, they don't allow any of the wave energy to come through except right here. Now, you would think if we didn't have diffraction, that wave would just go straight down here and you would see like a straight line of the waves from the ocean going through. But what happens is it bends around here. Okay. So it can occur at the edge of any type of object. Okay. And so here's an example down below. If I have a source in like a waveguide, okay, and what will happen is that it doesn't just shoot out the waves straight out that pipe like a laser. What happens is it actually bends on the edges. Okay. Now, the calculations for this are very, very complex. And so we're not going to do a lot of calculations in this, even at state and nationals. But the thing to understand is that whereas refraction was bending at the interface of two materials, this one is bending around a corner. This is also why shadows are not very sharp. Okay. So if somebody puts on the light in the hallway and you're standing in a dark room and you can still sort of see stuff in that room, the light's diffracting around there, and that's what's bouncing off and allowing you to see stuff in that room. Now, we'll also get into single slit and double slit experiments, which were shown is how they develop diffraction patterns. And you can sort of see the bending of the waves. You'll also notice that there are certain places where the waves seem stronger and certain places where the waves seem weaker, and that's caused by superposition, which we'll also discuss later. So let's talk about superposition and interference. So what that says is basically for linear systems like waves, they add and or subtract. So if I look up above, I have the red and the blue waves, okay? And you'll notice that sometimes they add and sometimes they subtract. So the black is just adding both of those waves. Now, this particular one, it seems like for the most part, it is they are in sync such that the amplitude is much higher for the superimposed wave than for the individual wave. So that would be what we call a constructive type of interference. And so if you'll notice here in two waves in phase, when I add wave 1 plus wave 2, the amplitude's double that. Okay. All right. Now that can be very, very useful if we're trying to do things where we want to increase the amplitude. Okay. The other thing is that I can actually put two waves 180 degrees or exactly out of phase. Now when I add them together, they cancel each other out. So like right now I'm wearing noise canceling headphones. Okay. And it uses superposition. What it does is it hears the outside noise and then adds to whatever I'm listening to the inverse of that. So therefore, that noise is canceled out. Okay, and it's used with destructive interference. Let's now talk about polarization. Okay, so you remember before when we were talking up top where it says linear polarization here, and we were talking about how the E field's going up and down in Z, up and down in Z. And then the B field, the magnetic field, is going left to right in the x and minus x direction, and the propagation is in the y direction. We use the right hand rule to figure out the direction. So that's very standard. But you can also have other types of polarization. Sometimes they're not exactly lined up with the x, the y, and the z coordinate system. It's a lot more complex. And in fact, a lot of times what you'll do is you'll rotate your coordinate system around so that they do line up exactly like that, just to make your math easier, and then you rotate it back at the end. That's one way to do it. Another situation that can come up is, what if you have circularly polarized waves? And what I want you to notice here is circular polarization. It goes like this, okay? And what you'll notice here, okay, is that with circularly polarized waves, okay, the polarization that they're discussing is usually the electric field, okay? And so you will have circularly polarized waves. Light loves to do circular polarization. You'll find out that sunlight can be scattered by aerosols in the atmosphere, okay? And again, it all comes down to these polarizations, okay? Now, what you'll also find out is that depending on the type of polarization is going to determine what type of antenna I might use. So I might use, like if I'm going to do a radio station, I want to use a vertical polarization. So that's why if you have one of those old cars and the radio antenna, it goes straight up and down. Whereas if you have one of the old TV station antennas, they went side to side. Okay, and that's because they used horizontal polarization. And if you match up the polarization, things tended to transmit better. Okay, you can also convert circular to linear polarization, and you can see in the example off here to the right, they actually took a string and they had it circularly polarized, but then they put it through a little device that wouldn't allow it to go up and down. It only allowed it to go side to side, and it turned into a linearly polarized wave. And by the way, they can do the same thing with light with particular types of sunglasses. And if you ever go fishing, you hear about like polarized sunglasses. And what it does is that it knows that most of the light that's reflecting off of the water is going to be polarized a certain way because of Brewster's angle. And since it's only polarized one way, if I create a sunglass that is polarized the other way and only lets that through, I only let through a fraction of the light. And I can block out a lot of the UV and other damaging light to protect my eyes. So, for homework, I want you to put together all your formulas for speed of light, Snell's law, law of reflection, and the wording for Maxwell's equations that makes sense to you. Get at least 10 spectrum charts in your binder now, okay? Be able to find quickly what the speed of light in free space is, and what's the speed of light in water. Is it faster or slower? Get the table indices for refraction and get it for as many materials, but especially for common ones that transmit light, like air, glass, water, crystal, diamond. Thank you so much. And I hope this was helpful to everybody. And we'll go on to the next one.